Bismillahirrahmanirrahim. Today, inshallah, I'd like to talk about one of the last topics that we need to cover in this chapter, and this is about convergent and divergent sequences and series. So there's this concept about a sequence or series being convergent or it is being divergent. Now, although this applies to both sequences and to series, we're going to talk primarily about series because sequences in a way is a precursor or series are an extrapolation of the concepts of sequences. So here what we're going to talk about here applies to both sequences and series, but we're going to focus on series because conceptually the same concepts apply to both, inshallah. So it's best, I think, to try to dive in and try to illustrate this concept of convergent or divergent series as thus. So I have here for you three examples of three, and they happen to be all geometric series. So, so the first one is this one. Let's try to write out the first few terms for each of these. Okay, so the first term, see, this goes from n equals 1 to infinity. Notice all of these are infinite series. Okay, so they keep going forever. So let's write out the first few terms of this one. So the first term here would be a sub 1 is going to be 3 times 2, and n is 1, 1 minus 1. So that is 3 times 2 to the power of 0, which is 1, which is 3. And if you recognize, in fact, that this is a geometric series, and if you recall for geometric series, the empirical rules a sub n equals a sub 1 times r to the n minus 1. Okay, so the common ratio here, if you recognize, is going to be 2. So 2 is the common ratio. Let me write that over here, common ratio. So, and then if you recognize this to be the in the spirit of geometric series, in the form of geometric series, a sub 1 r to the n minus 1, then the common ratio is that. Okay, so let's write a few more terms, and if you recall, geometric series are generally basically multiplied by the common ratio. The next term is going to be, I can tell you it's going to be 6, because it's going to be multiplied by r, and I can tell you that the next term is going to be 12, because there's a common ratio is 2. Okay, that's that r over here. But let's just do it in a long way. So the second term would be a sub 2 is going to be 3 times 2 to the 2 minus 1. So that's 3 times 2 to the power of 1, and that is 6. So we got that. So let's write down 6 over here. So we have 6. Now we now recognize the common term ratio is 2. Every term is going to be multiplied by 2. And this is going to be 12, and that's going to be 24 plus dot 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 to infinity. Now this is an example of a divergent sequence. Okay, so this is a divergent series. Okay. So this is a divergent series. How is that? Okay, the reason it is because the numbers getting bigger and bigger and bigger. Okay. Now the concept will become quite clear, I think, by the time we're done with writing these three. Now look at this one on the other hand. This is also, if you recognize, the geometric series where a sub 1 is actually 1 times the common ratio is 1/2 to the n minus 1. I picked these because we're familiar with these. But so let's generate nevertheless the first few terms of this series. So the first term is n is 1. It's going to be 1 minus 1 is 0. It's going to be 1/2 to the 0, which is 1. The next term is going to be, when n is 2, it's going to be 1/2 to the 2 minus 1. That's 1/2 to 1, which is 1/2. So that's the next term is going to be 1/2. So let me just write that. Try to keep this clean. 1/2. And then the next term, if you put 3 over there, and then you recognize it's going to be 1/4, and the following term would be 1/8. Okay, because in all of these are geometric sequences, a series, so it's going to be the common ratio is 1/2, 1/2, and 1/2. But if you weren't sure, you could just like write them out like that. So if you continue like this and keep going, and you can see the numbers here are getting smaller and smaller and smaller, okay? So, and this is a convergent sequence series. Okay, that's pretty interesting. Now before we go on to the third one, let's see if we can just like graph these. Okay, not erase all of them. So if I were to like graph this, so let me make a graph over here, perhaps. Okay. All right. So if I were to graph, let's say the first one over here. When n is 1, it's like 3, and then it gets bigger, 6, and it's bigger like this. So it's kind of like, you know, like going higher and higher and higher like that. The second one, however, it starts out at 1, 1, and it gets 1/2. I mean, this is not to scale, obviously. So as you can see, it's getting closer and closer to 0. So it's converging. And hence the term. It's converging to 0. So it's kind of approaching or converging to 0. So this is a convergent sequence. Now it's kind of like an asymptote. It converges there, but it actually doesn't quite reach it there, right? It never ever becomes 0. So it's converging to 0. Okay, where it's not converging to anything. So the concept of convergent is that it approaches. So convergent sequences and series, they approach. So they approach or converge to a particular number. Now it doesn't have to be 0, it could be any number, but they converge to 0. Now look at the third example here. Okay, now this is an interesting twist to the concept. Now let's write the first few terms. When n is 1, it's negative 1/2 to 1 minus 1. That's negative 1/2 to 0, and that's 1. So the first term is 1. The second term, with a sub 2, is when n is 2. It's negative 1/2 to 2 minus 1, and that's negative 1/2 to 1, which is negative 1/2. So the second term is actually a negative term. All right, so, and then the third term, a sub 3, is negative 1/2 to 3 minus 1. That's negative 1/2 to 2, and this is positive 1/4. So it's a positive term. And then the fourth term, a sub 4, is negative 1/2 to 4 minus 3. That's negative 1/2 to 4 minus 1. Yes, 1/2 to third, sorry. And that's negative term, negative 1/8. Okay, so plus negative 1/8. So you can see, and positive and negatives are alternating. The next one is going to be positive 1/16, and the next term is going to be negative 1/32. And it'll keep going like this. So now this is an interesting series, because it starts out, let's say, at 1, right? And then it goes to negative 1/2, and then it goes to positive 1/4, and negative 1/8 positive. So it's doing one of these. It's going from here to here to here to here. But nevertheless, even though it's kind of vacillating between across from the x-axis, it converges. It's converging to 0. So this too is actually a convergent sequence, okay? A convergent series. So this one is a convergent series, and this one is a convergent series. So the concept of a series converging is that it is a series converges if it approaches a certain number. Okay, so that is the concept of a convergent versus divergent sequences or series. And this is a very, very important concept. So I gave here examples of geometric series, but they could be non-geometric series, and they could still converge and they could still diverge, of course. Now, there is an interesting concept that results from this, and we shall talk about this in, next. So now look, we have seen this before. This formula is a sum of a partial sum of a geometric series. Okay, so when we talk about series, okay, and the sum of series, we can talk about partial sums, and we can talk about the sum of infinite series, or sum of all the numbers. Here's what I mean. So let's reconsider. Consider again this series which we talked about. Now, when we talk about sum, we can talk about a partial sum. A partial sum of a series is the sum of a certain number of terms. Let's say the first 4 terms, or let's say the first 5 terms. Okay, to do this, you use this formula. So this formula that we have learned before and that which we have derived before is the sum, the partial sum. And that's why the n is there. So however many n terms there are, this formula will give you the sum of those n terms. If you wanted to find the sum of first 50 terms, you would put n to be 50. If you wanted to find the sum of the first 71 terms, you would put the 71 over there. Now, the interesting thing that happens, though, is that what if somebody said, okay, I want the sum of the whole series, all of it. But then you would say, you know, that's impossible. The series goes on forever and ever and ever. But actually, even though the series goes on forever, you can actually find the sum of all of the series, the terms of the series. And the formula is actually quite simple and quite elegant. So now the formula turns out is very similar to this. And the formula for the infinite sum, the sum of an infinite series, is as simple as this. Formula is the sum is a sub 1, okay, over 1 minus r, and that is it. In other words, if somebody asks you to find the sum of this particular series, what you would have to do is you would have to put the sum, the a sub 1, over here, and over 1 minus the r, and the common ratio is -1/2, so it's like this. So, and this is going to be 1 over 1 plus 1/2, right? So that's 1 over 3 over 2, okay? So 1 divided by 3 over 2, right? And that's going to be 1 times 2 over 3, okay? That's 2/3. So all of this sum will add up to 2/3. All those infinite numbers will add up to 2/3. Okay. Now that's sometimes difficult to put your mind around it, but you can actually find the sum of infinite geometric series like this. Or now, but you have to understand what kind of geometric series converge and what kind of geometric series do not converge. Okay. So what do you think? What kind of geometric series converge and which ones do not? Okay, well, if I give you this geometric series, this is 1 plus 1/2, multiplying every number by 1/2. This is 1/4, so the common ratio is 1/2 times 1/2 plus 1/8 plus 1/16, and you can see the numbers are getting smaller. Right, so that these will converge. So this series is going to converge to 0. And on the other hand, if I give you this geometric series, the common ratio being 2, so that's 2 plus 4 plus 8 plus 16. So common ratio is 2, like this. So this is a divergent series. So you can see when the r value is when the r value is less than 1, it will converge, or has to be greater than -1, because it could be just a negative number as well. And an example was the -1/2 to the n-1 series, right? Because it vacillated between the x-axis, eventually converged to 0. So the series that converges is r, where r is between +1 and between -1. Anything outside of 1 and anything outside of -1, the series will diverge, correct? Another way of writing the same thing is the absolute value of r has to be less than 1, and the series will converge if this is the case, because this basically is another way of simplistically of writing that original thing. So here are the three formulas. First formula is the partial sum of a geometric series of n terms. Then you take a sub n, 1 minus r to the n over 1 minus r. Okay, let me try to write that a little neatly. 1 minus r to the n over 1 minus r. So this is a partial sum. And the infinite sum, or sum of the entire sum, or the sum of the infinite series, is, you don't write n over here because we're basically doing infinite n's. The sum is going to simply 1a over 1 minus r. Now, we don't have the tools to try to derive this or to talk about it even at this stage, and so in the future we will be able to talk more about this. But this formula is really a simplification of this formula. What happens, if you recognize, is if r is a small number like 1/2, okay, this term becomes essentially 0 as then this term is going to get 0. For example, 1/2 to 1,000 is going to be essentially 0. So this term basically drops out as n gets bigger and bigger and bigger, and when that happens, this formula simplifies to 1 minus 0 over 1 minus r, which is a sub 1 over 1 minus r. So this is a partial sum of a geometric series right here. Okay, and this is the sum of infinite geometric series. Okay, and but then you have to understand where r, the absolute value of r, has to be less than 1. That's how you know that the series converges. So this was our introduction to convergent and divergent sequences and series. I hope you enjoyed. Until next time, as-salatu was-salamu ala rasulillah. Assalamu alaikum. Talk to you then.